Okay, welcome back to the last lecture of today's session. The next talk will be about measurement-induced phase transition in a quantum Ising system by Professor Dasgupta from the Harish Chandra Research Institute.
Thank you. So let me thank the organizers for giving me this opportunity of presenting my work. So the title is Measurement-Induced Phase Transition in a Quantum Ising System. I am from Harish Chandra Research Institute, and formerly I was in the University of Calcutta. My collaborators are Paranjoy Chaki from the same institute, who is a PhD student, Pratush Nandi, my PhD student in University of Calcutta, and Ujjal Sen, a faculty of this institute. Okay, so this is the outline of my talk. I will start with a brief history of this MIPT, Measurement-Induced Phase Transition, and then I will describe the measurement protocol for our scheme, the work I will describe. And then I will present a derivation of some recursion relation for survival probability. And this will be followed by the results for survival probability and what we call the transition and the characteristics of the transition. And then I will present some scaling of the results with respect to size of the system. Lastly, I will discuss the relation between this measurement-induced phase transition and quantum phase transition. Okay, so history. Suppose you search in archive these three words, measurement plus induced plus transition, then you will get 108 results. So the last result, the 108th result will be measurement-induced quantum classical transition. It is not the one what we understand by measurement-induced transition nowadays. And this is also a somewhat different thing. This is also a somewhat different thing. And what we understand by measurement-induced phase transition is first seen in number 100. So this 100 is measurement-induced phase transition in a quantum spin system by myself and my PhD student. And then 99, 98, and in 97, you will find the famous paper by Skinner, Ruhman, and Nahum, which has got 850 citations till now. And then there came the works of Chen and Fisher in 2018, in 2019, and this is an experimental paper which was published in Nature Physics, and maybe hundreds of more other papers which came afterwards. So this topic is not very old. It started in 2016 or rather 2018 or so. Fine. So the system we shall deal with is a chain of n Ising spins plus minus 1. It's a chain of Ising spins, and the number of Ising spins is n. Suppose I take a chain of Ising spins which are all up initially, all oriented in the plus z direction. And then we let it evolve for some time interval tau under some Hamiltonian. This Hamiltonian is the transverse Ising Hamiltonian, which contains nearest neighbor interaction in the x direction and a field in the transverse direction, field strength being h. And after this evolution, we perform a measurement. The measurement is, are all spins up? And this measurement will give me a binary answer, yes or no. So we perform measurement at each time step with certainty. So there is no probabilistic issue. And we repeat this thing. So this thing, evolution under the Hamiltonian and performance and this measurement, this will be repeated. So we have introduced two parameters till now. One is the time interval over which this system will evolve, and then the field strength of the Hamiltonian. So these two are the two parameters of our study. So this is the scheme. We started with this system of n Ising spins, all oriented in the plus z direction, and then unitary evolution under this Hamiltonian, transverse Ising Hamiltonian for time tau, and then measurement are all spins up. Suppose the probability with which it is yes is P1, and then the probability with which it will be no is 1 minus P1. So again, we make a unitary evolution for time tau, followed by a measurement. And in the second case, if I get yes with probability P2, then the net probability of getting no till now is 1 minus P1 minus P2, so that the sum of everything is 1. And so this thing is repeated. So after n steps, probability that the answer is no for all these n steps, all the first n steps, is survival probability, which is 1 minus P1 minus P2, etc. So this is a key quantity. We shall deal with this survival probability. Now, so we have started with this initial state, I, where everybody is plus. And in the first time step, there is evolution over time tau. So I get e to the power minus IH tau operating on this state. And then this measurement is performed. So P1 is just this I times this operating on this thing mod square. And the wave function for no, I mean, wave function describing the replicas, which has given me the answer no, is this, this thing from which the component of I has been projected out. So we take this thing and project out the component of I. So this is the wave function for the replicas, which has given me no. And in the second case, again, in the second time step, this psi1 will be evolved over time tau. And I will get yes with probability P2. And the wave function for no will be this thing, e to the power minus IH tau operating on psi1 minus this initial state projected out. So in the nth time step, it will be the previous wave function evolved over time tau. And from this component of I is projected out. So the survival probability is the probability of getting no for n time steps, as I defined in the previous slide, is this psi n mod square. And this we denote by Rn. So we have derived a recursion relation for the survival probability. So we have started with this. This is our initial state. Now we have defined a function phi n, which is e to the power minus IH tau n operating on I, and a scalar Fn, which is the matrix element of this thing between the initial states. So these two things we define for n equal to 0, 1, 2, all values, all integer values. Then obviously phi 0 is nothing but the initial state. And these phi functions are not orthogonal. So the inner product of phi m and phi n is this number, is this scalar f. So after the first time step, this psi1 is only phi 1, which is just e to the power minus IH tau operating on I, minus f1 times I, just from the previous slide. Just the same thing which I have written here, only introducing these new terms phi and f. So after the second time step, we will get a similar expression. Now note that psi1 is a function of phi1 and I. I mean, psi1 can be written as a superposition of phi1 and I is phi 0. So it's a superposition of phi1 and phi 0. And psi2 is a linear combination of phi 2, phi 1, and phi 0. So the basic idea of the recursion relation is that for n equal to 0, 1, and 2, we find that the wave function can be expressed as a linear superposition of the phi m's, of the phi vectors. And the coefficients are written as Cmn, where the superscript n stands for the nth wave function, and m is the successive m values. And from these relations, one can write down the initial first few C coefficients. So this gives me this fact that psi n can be written as a linear combination of phi m's for n equal to 0, 1, 2. And then we prove by method of induction that if psi n can be written in this form, then psi n plus 1 can also be written in this form. So psi n plus 1 is just e to the power minus ih tau operating on psi n minus this thing, as I had written before. So after a little algebra, you can find that this can also be written in this form as a combination of the phi vectors, where these coefficients obey some recurrence relations. So the recurrence relations are these. Now note that C is C times a summation over C into F. So if you know all the C's and the F, then you know a future C. So in order to find C for superscript 5, you need to know all the previous C's and F. If you know F1, F and C of C superscript 1, 2, 3, 4, then you can find C superscript 5, all the C superscript 5, all the coefficients. So using the expansion of wave function in terms of the phi functions, one can now express survival probability after n measurements as this thing, because psi n is this thing. So I just have to take complex conjugate of this and then take the inner product. So one gets this thing. And these are some initial coefficients and some identities which can be easily verified. The crucial point is if all the Fn are known, then all the coefficients for the nth stage is also known. So these expressions are valid for any Hamiltonian and any initial state, provided all the Fn are known. Whether Fn can be calculated in closed form or not is a different question. So we are using transverse Ising model, and so for us, for the specific case of transverse Ising Hamiltonian, one can derive an expression for this thing in closed form for any even value of n. Any even value means not necessarily large, even 4, 5, 8, etc., 4, 6, 8, etc., any even value of n by using the known exact solution. So one can, it's just a simple algebra. So one can find that Fn is actually a product over some wave vectors, k equal to 0 to n. And there are n by 2 such wave vectors, which are spaced by pi by n and which are odd multiples of pi by n. So this is a product over k values. And some new quantities have come in. One is lambda k and the other is theta k. This lambda k and theta k are functions of h and k. So numerically, one can calculate Fn for any n. Because suppose I take a system size of 100 and then I know that my k values, there will be 50 k values. So one take a product over 50 k values and so on. Now, in principle, one should be able to calculate the survival probability for any system size and time state. But due to precision problems, we had to be confined to sizes less than 1,000. We could not exceed 1,000. Maybe we are still trying to extend this limit. And time steps also, we could not go beyond 10,000. There was some precision and an issue of numerical error. So how do the survival probability look like? So here we have plotted survival probability versus time step. You see, there is a plateau region and then some rugged decay, region of decay. Here also a plateau region, and this is a plateau region. This I call a plateau. This is too small. There is no plateau region here. This is a plateau region. When there are several plateau regions, I take the first one. And then a decay. So this is the result for 50 and 70, for h equal to 0.5 and 1.5. These two values are significant because one is less than 1 and the other is greater than 1. And we know that, sorry? because we know that when h is less than 1, then the ground state of this Hamiltonian is ordered, and when it is greater than 1, it is disordered. So I just show two cases for the two types of ground state function. What are the characteristics for h equal to 0.5? We discussed this case first, when the ground state was ordered. There is a plateau region, as I mentioned before, and this region increases in size as this tau, this time interval, decreases. So this is 0.2 and this is 0.1, and you see this region has increased a little bit. And also as the system size increases, so if you plot it for 70, you will find a longer region, much longer region. Now the question is how this height of plateau region varies with this time interval tau. H increases actually monotonically with tau, but the rate at which H increases with tau is interesting. The curve of dH d tau versus tau shows a peak. And as I said, we could go up to a size of 1000. So the curves look like this. You see, this peak is important, as we shall discuss in the next slides. And this sharpness of the peak and position of the peak depends strongly on the system size. And you can guess that some issue of scaling with respect to system size will arise in future. But what is the significance of this peak? What happens at this peak? So here is a plot for small sizes, 20, 22, 24, 26, 28. There we could exactly numerically calculate the state and calculate also the entanglement and other properties. So you see here also this position of the peak slightly shifts to the left as the system size increases, and the shift is detectable even in small size. When it goes from 20 to 28, there is a reasonable amount of shift. So as system size increases, the peak becomes sharper and higher, and at the peak, there is an area law to volume law transition in entanglement. So at this peak, there is an area law to volume law transition. Hence, we identify this peak with the transition, and we call this location of this peak as the critical value of tau, namely tau c. It's because here is an area law to volume law transition. Now, here is a brief, just one-page summary of this paper by Skinner and Ruthman and Rahom. So they had taken a quantum circuit with random unitary dynamics. So at every time step, Z component of spin was measured with probability P, and they found that the volume law exists for P less than PC, some critical value, and area law for P greater than PC. So P is the probability of measurement. And see, in our case, tau is the interval between the two measurements. So in a given time interval, I make more frequent measurements, and the measurement becomes more probable when my tau is smaller. So large P basically corresponds to smaller value of tau. And the Skinner and Ruthman and Nahum had shown some scaling plots. This is the bipartite entanglement and von Neumann entanglement entropy between the two halves of the system that shows a collapse for P greater than PC when S at P minus S at PC is plotted against this quantity. So there is a collapse up to this 0. 0 means P equal to PC. After that, the collapse is gone. So we have followed blindly, quite blindly, this scheme, and we have measured this. For our system, we have computed von Neumann entanglement entropy between the subsystems of size L by 4 and 3L by 4 for system size 20 to 26, and find a collapse for tau less than tau c when this thing is plotted against this, just as Skinner did. So there is a collapse And if you do not like the quality of collapse, actually we are trying to go to L equal to 28. There is some memory problems, but we are hopeful to get a better collapse when we can include this. Yes, please. And this is the, yes, no clicks. No clicks, yes. Yes, Skinner works. So this shows that there is a volume law to area law transition in this case. Now the thing is, the peak moves to the left as the system size increases and becomes more and more sharp. You see? And one can find numerically that there is a scaling of tau proportional to 1 by square root of n. So curves for different n's, all these curves, they collapse on each other. They're indistinguishable. If we use as variable not tau, but tau into root n. So here we have plotted, here x-axis is tau into root n, and this derivative is dh sigma. So sigma is the new variable. If we use the scaled variable, then all these curves fall on each other. And so one important thing is, as n goes to infinity, tau c becomes 0. So that means the transition we are studying exists only for finite size. And in the thermodynamic limit, there is no transition. And in the thermodynamic limit, there will be only volume law in the entire range. There will be no region with area law. So this is all for the transverse field 0.5, which is in the region of ordered ground state. So we now discuss the characteristics for H equal to 1.5 when the ground state is disordered. Again, there is a plateau region.
Sorry, one question. The 0.3 exponent you had.
Yes.
Is that related to their new this exponent 0.3 over here?
Yes.
Was it related to their 1 over nu p minus pc?
Yes.
What is the relation?
No, this 0.3 is, okay, 1 second.
So if you go back to their thing, their 1 over nu, yeah.
1 over nu. So 1 over nu is here 0.3, but we cannot comment why it is 0.3 or any other. What is your question?
So what was it for them? What was new for them?
For them, it was.
Or is there any relation between their 1 over nu and?
Yes. I've forgotten. I have to check. I've forgotten. Sorry. Yes. So, when I take a field value of 1.5, there is a plateau region, and this again increases as tau decreases and the system size increases, the same feature. And this also shows a peak. As system size increases, the peak becomes sharper again and becomes higher and moves to the left. And we again find a area law to volume law transition at tau c, at the peak of the curve. So these peaks are marked by a area law to volume law transition for small size. Of course, Of course, this is for 100, 200, etc. We cannot calculate entanglement for these cases, for this system size. We have calculated entanglement for 20 to 26, and that shows a area law to volume law transition. For this value of field also, there is a scaling, but the scaling is not so good. It is good only for large sizes, for 100. This is the curve for 100. This is 200, and 300 and 500,000 and 1,000 are mostly coincident. Again, at n tending to infinity, tau c is 0. So in the thermodynamic limit, there is no transition. The transition exists only for finite system. This scaling relation can also be derived analytically, because the survival probability is this. This is from my previous slide. This was the expression for survival probability. and the recursion relation was this. So you see the coefficients were F. F coefficients were important, and the expression for the F coefficients was this. So to derive this scaling relation, we write this quantity Fn. This quantity is only of central importance. We write this Fn as rho n into e to the power phi n, where phi n is the phase factor. And then rho n becomes this thing, just a straightforward application. And the expression for phi n is this. Now the important thing is for small values of tau and n, this lambda k n tau will be small. And so I can replace tangent of this thing by the argument itself. And so lambda k cancels out and I'm left with n tau. And then there is h plus cosine k. And well, if the things are small, then I can remove this tan inverse term also. So summation over k of cosine k will give me 0. And so this phi n will be some constant, this mu times small n, where mu is 2 tau h n. And this shows after a little bit of algebra that argument of the coefficient c is just n minus m, some constant times n minus m. So argument of this summand, this quantity which is summed over m1 and m2 in the expression for survival probability. This quantity, argument of this quantity is 0. So we only need to bother about the modulus of R because the argument gets cancelled out. Fine. So the modulus of R is only the modulus of Fn matters. So in the limit of small tau, this modulus of Fn takes this form. So we can conclude that tau and n occurs in the combination in the form tau square n in the value of survival probability. And hence that scaling of tau as 1 by square root of n. This was all about this measurement-induced phase transition in our model. Now I just discuss briefly the relation between quantum phase transition and measurement-induced phase transition. Normally, measurement-induced phase transition may not always be related to the quantum phase transitions. Here we find that when the ground state is disordered, then the survival probability versus time step curve has a logarithmic decay. But this logarithmic decay is absent when the ground state is ordered. So this measurement-induced phase transition and this survival probability, it can sense whether the ground state is ordered or disordered, and it depends on the value of h, on whether h is in the ordered regime or disordered regime. However, it's not true that in the entire disordered region I find logarithmic decay. When h is too high, say 3 or 4, then the logarithmic decay is not there. But immediately after 1, there is a logarithmic decay. That's one. That's all about this thing. And now another analytically tractable measurement-induced transition. This is our that 2016 paper, which was number 100 in the archive list. So here at each, I mean in whatever I have discussed till now. So whatever I have discussed till now, at each measurement, we have removed the component of initial state and retained other states. Now suppose we do the reverse. So suppose we retain the initial state only, then something more straightforward happens. So this was our 2016 paper. I have written it in red because this is not a Dhar, and if somebody finds a mistake here, poor a Dhar is not responsible. It is some other Dhar. So we start with this initial state, and after the first time step, the wave function is a scalar times this thing, where the scalar is this thing. And after the second time step also, this ratio will be the same. So it will be an exponential decay. So this factor P will be the same at every time step. And in the nth time step, it will be P to the power n times the initial state. Then what is so important, what is so interesting here? because the expression for P can be calculated exactly. And the expression for P can be written in terms of an integral, etc. And one can find analytically that there is a non-analytic behavior of alpha whenever this condition is valid. So you take any HC less than 1 and calculate tau C from here, then you will find a kink at that HC, at that tau C. So let me show the curves. So here is the plot of alpha. Alpha is this thing, this coefficient, alpha n tau square by 2. You see here also I find that scaling, that combination n tau square. So the probability is e to the power minus alpha n tau square by 2. And if I plot this alpha, then what I get is this alpha versus h shows some kinks for different values of tau. There is a discontinuity here. There is a change of slope, sharp change of slope. And one can calculate analytically the change of slope, the change of slope at these points. And if I plot this alpha with respect to tau also, there is a kink. And at every kink, one can calculate this change of slope analytically. And we may call this phase transition because there is non-analyticity at the thermodynamic limit. However, this P vanishes in the thermodynamic limit. So again, this is a phase transition and for finite size only. This is not a transition for infinite size. And lastly, at every stage, only the all up state is retained. Hence, a study of entanglement is not meaningful because at every stage I am only 4 minutes left to 40 minutes. Okay. At every stage, all up state is retained, and hence a study of entanglement, the question does not arise. Fine. So summary. We present a protocol for measurement-induced transition where at each time step we evolve a quantumizing chain under transverse Ising Hamiltonian for time tau and then make a global measurement with certainty. For system size less than or equal to 28, there is a transition entanglement at some tau C. We also calculate survival probability of the initial state and find that a quantity, a derivative of this thing, derived from this probability also shows a peak at tau C. So using some recursion relation, so you see the logic is there is an entanglement transition at tau C and we get a peak for small size in survival probability at tau C. So, but we cannot calculate entanglement for system size 1000, but we can calculate the survival probability dH d tau for 1000. So we argue that this transition, this peak should correspond to a transition for large size also. So we find that there is a scaling tau C 1 by root n, and hence the transition occurs for finite size only. So it will be interesting to investigate the size dependence of the critical point in other measurement-induced transitions. We also find that the behavior of survival probability has some relation to the order present in the ground state of the Hamiltonian. So that's all. Thank you.
Thank you for this very interesting talk. Are there questions?
Can you explain more intuitively what is the connection between the survival and the entropy? Why do they have the same? There is a correlation between the two quantities. I see this, but I don't really understand why.
We don't know, basically. We don't know why the entanglement transition corresponds to some peak in the derivative of survival probability. No.
Yeah, so just to understand, I mean, so you're looking at the entanglement after doing the no-click dynamics for a long time, right?
Yes.
Is that, so it kind of reaches a steady state and then...
steady state, yes.
It's probably some eigenvalue of some non-Hermitian, there's some 0 or
Yes.
largest, I mean, eigenvalue, right? And
So
so
you mean survival probability should be eigenvalue of some non-Hermitian matrix?
because it's a no-click dynamics. So
Yes,
then you have
because
some
it's a no-click
corresponding.
dynamics, yes.
So then, and if your final conclusion is that in the thermodynamic limit, it's a volume
Law
entangled
persisting everywhere.
state. Oh, right, okay. Okay, no, that means it's, okay, I mean, I'm wondering what the steady state looks like. Like, is it a kind of close to a thermal state? Or?
It's a thermal state or not. Why should it be a thermal state? Because there is volume law.
Maybe it's not a thermal, but at least it's volume law. So it might be some effective thermal.
Yes.
The other question was you never looked at the critical point. Is it you looked at H greater than 1 and less than 1? But the critical...
Yes, we didn't look at it. Those studies are under studies, and we are making the H exactly equal to 1, what happens. And you see this critical point tau c, that even for small size, you see here tau c is 0.1 for small size, 20 to 26. For 20 to 26, it is 0.1. When H is when H is 1.5, I guess, yes. But when H is 0.5, it was 0.2. So a question is whether it changes from 0.2 to 0.1 abruptly at H equal to 1, abruptly at the critical point, or it changes slowly. These things are under investigation now. We have just put it into archive yesterday, today. It came to archive today only.
Sorry, just
yes,
in the conclusion, when you said L less than 26,
yes,
you mean up to size 26?
Up to size 26.
Up to size
20 to 26.
20.
Because below 20, the curves are very erratic.
Okay.
Inconclusive, actually.
Just one very quick question. So in the initial calculations you presented, in the calculation steps, it was nowhere you relied on the fact that psi is not normalized, right? I mean, your psi ends are not normalized.
Not normalized.
But then when you wrote it as linear combinations, all that is fine even though it's not normalized.
Yes, yes, yes.
Just in terms of mathematics, it was.
Yes, yes, yes.
Okay,
yes.
okay.
It's just straightforward algebra.
Okay, so it's not needed to be normalized.
It's not needed.
Thanks.
Let's thank the speaker again.
Thank you.